Oh no.
So remember that we can use derivatives for determining max and mins. So we'll do that with some equations involving trig functions. Position of a particle as it moves horizontally is described by the equation S equals 2 sine t minus cosine t, where t is between 0 and 2 pi. S is the displacement in meters, t is the time in seconds. Determine the minimum and maximum displacement. So recall that the min and max displacement occurs when the velocity is 0. And the velocity is the rate of change of displacement with respect to time, so it is the derivative of s, the position function. So if we start with s equals 2 sine t minus cos t, then we will differentiate with respect to time. The derivative of sine is cosine, so the derivative of 2 sine t will be 2 cos t, minus the derivative of cosine, which is negative sine t. So that'll give us 2 cos t plus sine t. And remember, our critical numbers occur where that equals 0. So to solve this, can't factor, but here's what we can do. We can move the sine t over to the other side by subtracting it, and then we can divide both sides by cosine t. So you'll get 2 on the left equals negative sine t over cos t, and sine over cos is tangent. So it'll be where the negative tan of t equals 2, or where the tan of t equals negative 2. Now in this case, it's not necessary to solve for t. We only want the sine and cosine of t. That's what we need, because we're going to plug those values into the original equation, our original displacement equation, which is 2 sine t minus cos t. So again, we don't need to know what t is, we need to know what sine t and cos t is. And we can get it because there are two quadrants where the tan of t equals negative 2. Two quadrants where tangent is negative. And those being the second quadrant and the fourth quadrant. And again, we know this because of our cast rule. Tangent is positive in the first and third quadrants, so negative in the second and fourth. You with us, Brighton? Okay. So the tan of t, which is opposite over adjacent, and remember t is the reference angle, so opposite over adjacent will be 2 over 1, and in this case the 1 will be negative because you're going left from the origin. In the fourth quadrant, it'll be the 2 that's negative because you're going down from the x-axis. We can find the length of the third side by using Pythagorean theorem. So we're going to get 1 plus 4 equals c squared. C squared will equal 5, and c then will equal the root of 5. And the hypotenuse is always positive. So now we can get our two values for s. Our two values for s will come from the value in quadrant 2 and then the value in quadrant 4. The larger of those two values will be the maximum. The smallest of those two values will be the minimum. Again, we have s equaling 2 sine t times the cosine of t. In quadrant 2, The sine opposite over hypotenuse will be 2 over root 5. The cosine adjacent over hypotenuse will be negative 1 over root 5. So if you multiply those out, 2 times 2 is 4 times negative 1 is negative 4 over root 5 times root 5 is 5. Oh, I'm sorry, it should have been minus, not times. I apologize. It's 2 sine t minus cos t. So let's fix that. So this will be 4 root 5 plus 1 root 5. The minus minus becomes a plus positive, which will give us 5 over root 5, or 5 root 5 over 5 when we rationalize that, which becomes just root 5. And then in quadrant number 4, the sine opposite over hypotenuse is negative 2 over root 5 minus the cosine, which will be 1 over root 5. So that'll be negative 4 over root 5 minus 1 over root 5, negative 5 over root 5, which again, if we rationalize by multiplying top and bottom by root 5, we're going to end up with negative root 5. When we compare these two values, obviously this one will be our minimum displacement, and the root 5 will be our maximum displacement. Okay? Number 2, determine the maximum perimeter of a right triangle with a 20 centimeter hypotenuse. So we can change the lengths of the two legs, but what's going to stay constant is that the hypotenuse is 20 centimeters, and every time you change the lengths of the legs, you're going to get a different perimeter. So because we want to maximize perimeter, we need to come up with an expression for the perimeter that we then would differentiate. That's what we need to do. And the only thing we're told is that the hypotenuse is 20 centimeters. That's all we're given. So initially, let's start with the other two sides being x and y. The problem, though, is that they are in terms of different variables. So we need to somehow write an expression for the perimeter in terms of only one variable. And here's how we can do that. If we let this angle at the bottom be theta, then we can write an expression for the sine of theta. That will be opposite over hypotenuse, y over 20. So y will equal 20 sine theta. We can also write it a trig ratio involving x. That would be the cosine of theta. That's adjacent over hypotenuse. And the reason why we always want to use the hypotenuse here is because we know that side. That's a constant, so we're going to use that. And we'll get x equals 20 cos theta. So now we can write an expression for the perimeter in terms of a single variable, and that actually would be theta. PR perimeter will be 20 sine theta. Let's write it down here just so we have more room. plus 20 cos theta plus 20. There's an expression for the perimeter. And we want to find out the value of theta that will make this a maximum. So we differentiate. It'll be dp by d theta. So dp by d theta. The derivative of sine is cos, so that'll be 20 cos theta. The derivative of cos is negative sine, so that'll be negative 20 sine theta. And the derivative of 20, a constant, is 0. And we want to find the critical numbers for this, where it equals 0. So like we saw in the last one, if we add the 20 sine theta to both sides, we'll get 20 cos theta equals 20 sine theta. And then if we divide both sides by 20 cos theta, you'll be left with 1 on the left equaling tan theta on the right. The 20s will cancel, and sine over cos is tan. Where are you going? Test tomorrow, remember. Okay, so because theta has to be a acute angle, because this is a right triangle, so theta must be acute, the only place we're going to look at is where the tan of theta equals 1 in the first quadrant. And that'll be at pi on 4 radians. Now, we are told that we want to find the maximum perimeter. So that should occur at theta equals pi on 4. Like we've done before, we can confirm that by drawing a number line here. Put our critical number of pi on 4 in there and find the value of the derivative in each quadrant. Or not each quadrant, but in each interval. So in that first interval, we could use pi on 6. Remember, we want to find the value of the derivatives. And we can use our calculator to help us do this. Just have to make sure that we are in radian mode, which we are. So we can go 20 times the sine of pi on 6 minus 20 times the cosine of pi on 6. Gives us a negative value. So that means, remember, that the function that means it's negative. Did I put that in the right order? No, I didn't. It's 20 cos first. So let's change that. 20 cos of pi on 6. Minus 20 sine of pi on 6. So that is a positive decimal, which tells us that the function, the graph for perimeter, will be increasing in that interval between pi on 4 and pi on 2. So we can use pi on 3 there. So I can just go back and grab that same equation and change the pi on 6 to pi on 3. And we do get a negative value for that, which means the function's decreasing there. So that confirms that there is a maximum at theta equals pi on 4. And now we can find out what that maximum perimeter is by letting theta equal pi on 4 in our P equation. So P will equal 20 sine pi on 4 plus 20 cos pi on 4 plus 20. Now the sine and cosine of pi on 4 are both root 2 over 2. So it'll be 20 times root 2 over 2 plus another 20 times root 2 over 2 plus 20. So that's going to give you 10 root 2 plus another 10 root 2, which is 20 root 2 plus 20. And that'll be in centimeters. And so there's your maximum perimeter. Number 3, two sides of a triangle have lengths of 15 meters and 20 meters. The angle between them is increasing at a rate of pi over 90 radians per second. Determine how fast the length of the third side is increasing when the angle between the first two sides is pi on 3 radians. So notice it doesn't say anything about a right triangle because it's not a right triangle. So two sides have lengths of 15 and 20, and the angle between them is increasing at pi over 90 radians per second. So if we say that, let's say this side is our 15 and this side is our 20. Let's say our angle between them is theta. We want to know how fast the length of the third side is increasing. So if we label that third side x, we want to find what dx by dt is. We're given d theta by dt, the rate of change of theta with respect to time. That is pi by 90 radians per second. And obviously we have those two sides of the triangle. But we want to know the rate that x is changing with respect to time. So we need to come up with an expression that relates all these things together. And so taking you back to 20-1, you learned about the law of sines and the law of cosines. They are used in oblique triangles, triangles that are not right angled. In this case, we have two sides and the angle in between that we're talking about, and we also want to involve the opposite side. That is the law of cosines. The law of cosines says that in this case here, x squared will equal the other two sides squared and added together minus twice the other two sides times the cosine of the angle across from that. That's what x squared would equal, and that comes from the law of cosines. That might not be on your 4-minute sheet, but if you need it on a test, you'll be given it. It's the law of cosines. It's just an equation that you were given in 20-1. So you've got three sides of an oblique triangle, and this is used when you have two sides and the angle in between. And you want to find the third side. That's what this equation is used for. So the side you're looking for would be x, that is squared, and that equals, you take the sum of the squares of the other two sides minus twice those two sides times the cosine of the angle between them. That's what the law of cosine says, one of the variations of that. The other variation that you looked at in 20-1 was if you had all three sides and you wanted to find an angle. So it starts with this same equation, it just manipulates it to get cosine of theta by itself. But that's a law of cosines, and you did learn about that in 20-1. Now we can simplify this expression. 15 squared plus 20 squared is 625, minus 2 times 15 is 30, times 20 is 600 cos theta. Now remember, we want to get a formula that has dx by dt in it, as well as d theta by dt in it. And we can get that if we take this simplified equation that we're at right now, and we differentiate both sides with respect to time. So that means that you're using the chain rule. When you differentiate x squared with respect to time, it'll be 2x dx by dt equals, the derivative of 625, a constant, is 0. When you differentiate negative 600 cos theta, it'll be negative 600 but the derivative of cosine is negative sine theta times d theta by dt. So this will give us 2x dx by dt equaling 600 sine theta d theta by dt. And remember, we want to find the value of dx by dt at the moment when d theta by dt is pi on 90 radians per second. So we can take this expression that we've written and get dx by dt by itself by dividing both sides by 2x. So when you divide the 600 by 2, you'll get 300 sine theta over x d theta by dt. So if we look at this, again, we want to know what dx by dt is. We have it by itself. But to do that, we need to know both x and d theta by dt. We have the d theta by dt, but we don't have the value of x. But we want to find out what dx by dt is at the moment when theta is pi on 3 radians. So we can use the expression we have up in the top right-hand corner for the law of cosines to find out what x is at the moment where theta is pi on 3. So I'm going to use this simplified expression right there. X squared will equal 625 minus 600 cos of pi on 3 at the moment when the angle is pi on 3. And at pi on 3, the coordinates are 1/2 comma root 3 on 2. The cosine is 1/2. This is what x squared equals. Half of 600 is 300. 625 minus 300 is 325. And then we can take the square root of that to get x. So the square root of 325. So it's going to be an irrational number. We'll just leave it as root 325. So that's what x is. Now we can find dx by dt. (300) times the sine of theta, and again theta is pi on 3 over the root of 325 times d theta by dt, which is pi over 90 radians per second. So you just have to work this out now. The sine of pi on 3 is root 3 over 2. Over the root of 325 times pi over 90. So the 2 goes into the 300 150 times. And then we can divide the 150 and 90 both by 30. So that'll give us 5 up there and 3 down there. So what I have right now is I have 5 root 3 times pi over 3 root 325. Which I can simplify. If I rationalize the denominator by multiplying top and bottom by root 325, I'll have 5 pi root 3 times root 325 would be root 975 over 3 times 325. So there's a couple things that we can do here. The 5 on top and the 325 on the bottom can be simplified. 325 divided by 5 gives us 65 on the bottom. So we'll have pi on top right now. We'll have 65 on the bottom, which is multiplied by the 3. Gives us 195. We can also reduce the root 975. 975 is divisible by 25, which is a square root. So root 975 would be root 25 root 39. And then the root of 25 is 5, which we can cancel with the 195 below. 195 divided by 5 gives us 39 on the bottom. So it'll be pi root 39 over 39. And so there's your exact answer. It's the rate at which x is changing with respect to time. That's what it's increasing by. Okay, we're going to do number 4. We're not going to worry about number 5. There's nothing like that on the exam. So let's do number 4. A beacon is located a perpendicular distance of 315 meters from point R. So R is a point on the shore, and the beacon is a perpendicular distance of 315 meters from that. So there's B, the beacon. And that beacon revolves at a rate of 1 revolution per minute. So that would be theta that's changing, right? The beacon is moving. And as it's moving, it's shining its light along the shore. So d theta by dt is 1 revolution per minute. And 1 revolution around the circle would be 2 pi per minute. So we want to know, how fast does the beacon sweep along the shoreline? So if we say that that side there is x, we want to know what dx by dt is. So how fast does the beacon sweep along the shoreline at point S on the shoreline, which is 425 meters from point R? So if we say that this is S there, it's going to be at the moment when X is 425. But X is changing, right? It's not a constant. We want to find out what dx or d theta by dt is at the moment when x is 425. The 315 is a constant, though that doesn't change. So we want to relate this angle here with the 315, which is a constant, and side x, which is changing. And in relation to this angle, because this is a right triangle, those two sides are the opposite and the adjacent. That will use the tan. The tan of theta will equal x over 315. Or we can say that x equals, let's do it down here, x equals 315 tan theta. So we want to know what dx by dt is, and we're given d theta by dt. So to get dx by dt and d theta by dt in this equation, we need to differentiate both sides with respect to time. So the derivative of x with respect to time would be dx by dt. And when you differentiate 315 tan theta, the derivative of tan theta is sec squared theta. So that'll be 315 sec squared theta d theta by dt. So dx by dt is what we're trying to find. We're given d theta by dt. We're given what that is. We need to figure out what the secant of theta is, which secant is the reciprocal of cosine. The cosine is adjacent over hypotenuse, so we need the hypotenuse here. So c squared will equal 315 squared plus 425 squared, which we can use our calculator to get for us. So c squared will equal 279,850. And then c will be the root of that. Try that again. So approximately 529. That's an approximate, so I will keep that in my calculator. Because dx by dt will be 315. Now the secant of theta is the reciprocal of cosine. The cosine is 315 over our 529. So the secant will be 529 over 315. But that has to be squared. Times d theta by dt, which is 2 pi per minute. So back to the calculator we go. I'll take this number, I'll divide it by 315. I'll square it. I'll multiply by 315. And I'll multiply by 2 pi. So there's our approximate answer, 5582.06. And that would be in meters per minute. Our distances are in meters, and theta is changing at a rate of 2 pi per minute. So that's why it's in meters per minute. Okay? So we're going to stop there. You should work on these questions. I will post the solutions on Google Classroom so you can check your answers. You should also be working on that review sheet. Remember your test is tomorrow on this stuff. And then we have only one chapter left on integration, which is the opposite of derivatives. So we'll see how we find the integral of functions and what it is used for.